So let's take a look at the next page where we have a new motivation. Let's consider the following scenario and the associated question, and really try to think about what type of distribution does this scenario describe. All right, here we go. At a particular intersection, there's an average of 1.4 traffic accidents per week. And the question that we're going to have is, what is the probability that during the next week, no traffic accidents will occur? Well, I'm apparently interested in here in how many traffic accidents are going to be occurring at this intersection. I'd like a way to try to compute that and figure out the likelihood of different numbers of accidents happening. So what we can definitely say is that we can tell that this is a discrete distribution with, and we could say, x representing the number of accidents that occur in the next week, specifically at this intersection. Okay. Well, I can start to think about what we had said in the last several videos about what the geometric and the binomial distribution actually help us measure. Remember, we said that a geometric distribution is going to help us find a first success. And well, I'm not really interested here in trying to find a first success. Like, I'm not interested in when will the first accident occur. I'm also not really going to see this as a binomial distribution. Remember, that had the rhythm to it of something like, I want a number of successes in a certain number of tries. But here, I'm not like making attempts at accidents. I'm just kind of watching what happens during a period of time. So what we see here is that x is not binomial nor geometric. And so because of this, we're actually going to need another new type of distribution that we call a Poisson distribution. So here's the idea. A Poisson is another discrete distribution. However, it has the following kind of associated properties. The random variable x will always represent the number of occurrences of something, like the number of accidents, that happen in an interval of time, like a week, or sometimes in an interval of space, like maybe I want to know, like how many scuffs are there on the wall, right? So in a given amount of square footage, how many scuffs or marks do I see? So something like that is what a Poisson distribution is going to help us account for. Now, the probability of the event occurring, that is, of an accident occurring or finding a scuff on the wall, would have to be the same for each interval of time or space. And the number of occurrences in one interval needs to be independent of the number of occurrences in another interval. So this will kind of work itself into some of the checks that we'll have for our Poisson distribution. Now, a Poisson distribution has a very weird looking formula to help calculate it, but again, it's really just here to be scary. We're not actually going to utilize this formula. We'll use our nice calculator commands. X here is going to represent the same thing that it always has represented. It's going to essentially stand for either what value did we want our random variable to be, or in the CDF, what value of x did we want to stop at. Now, this value here is what we refer to as lambda. This is a Greek letter lambda. Okay? And that is going to represent the average rate of occurrence in an interval. Notice we were actually given that up above because we were told that there was an average of 1.4 traffic accidents per week. So we're going to see how we can utilize all of this information to answer a question like example number 3, and also see how this relates to what we see on the formula sheet. First, let's go ahead and flip over to the formula sheet just so we can make sure that we kind of record out all the information that we need for this new distribution type and see how this is organized on the formula sheet. So over here, you'll notice that we're now on this last column on the front side of the formula sheet, where we have our Poisson distribution listed out. So remember that a binomial distribution always asks us again about the number of successes in a number of trials. A geometric distribution asks for a first success, A Poisson distribution is going to ask for a number of occurrences in an interval, and that interval could be measured in terms of time or space. This is the goal here of what this is meant to do. Notice again there are two checks. The probability of the event occurring is the same for each interval, and the number of occurrences in one interval does not depend in any way on the occurrences in other intervals. The only parameter that we need to find is lambda. We can find averages and standard deviations, but we'll do that in a later video. And then I have calculator commands, Poisson PDF and CDF. Let's see how we can use these to go ahead and answer the questions in example 3. Let's see what we have here. Traffic accidents at a particular intersection. Notice this. I'm told they follow a Poisson distribution. Well, that's great. There's an average of 1.4 accidents per week. We will count the number of accidents that happen within a week. Okay, so when I go down here and I'm asked to define a random variable, notice again I'm starting right at the top of what the formula sheet would require. I'm always progressing from top to bottom. That's the easiest way to tackle these questions. So I'll start by identifying this random variable. So we'll again say, how about we let x represent the number of accidents that happen within a week. Okay, so a number of occurrences in an interval of time. We can already see that x has a Poisson distribution. And I also want to be able to state immediately what my value of lambda is going to be. Remember, lambda is always that average rate, and we're told that that's 1.4 accidents per week. I'll kind of abbreviate that like this, accidents per week. Okay, so let's take a look then at part B. We want to know what is the probability that the next week is accident-free. So meaning that the number of accidents that occur is exactly 0. All right? Well, that would mean that I'm interested in calculating a Poisson PDF. I can again think about this in the same way that we did with the geometric distribution. I can think about the fact that I'm going to have a nice table, although I don't fully have to draw it out every time, but in that table I'm going to have x's and p of x's. So x is the number of accidents that could occur. Well, there could be 0, maybe 1, maybe 2, maybe 3, maybe on and on and on. And right now, I just want the probability across from 0. So I can find that by doing a Poisson PDF, and I'm going to have my lambda value of 1.4 and my x value of 0. If I go to the calculator, this should crunch out the value that should sit right there in the table. That's the value I want. So let's switch over to our calculator to see what we get. Okay, so on our calculator, we can go ahead and click second, vars. Again, I'm going to scroll up, and you'll see down here I have Poisson, PDF, and CDF. I want my PDF command here, excuse me. I'm going to type in my value of lambda at 1.4, my x value of 0. This is what I should have already written down on my page, and here's my final answer. 0.2466 if I round to 4 places. So I'll write that out, 0.2466. All right, let's take a look at part C. What is the probability that there will be exactly 3 accidents next week? All right, so I want the number of accidents to be exactly 3. So that should be able to be computed by calculating a Poisson PDF with 1.4 and 3. If I go to my calculator and crunch that out in the same way that I just did, I should get a decimal value of 0.1128. All right, let's take a look at one more down here in part D. What is the probability that there will be at most 2 accidents? So the number of accidents is at highest 2. Well, notice that's really asking me to grab kind of these values off of the table and take the sum total of their mystery probabilities. Again, since I have a lot of these values, I might be able to easily grab them by using a CDF command. So this is a Poisson CDF. I still have 1.4, but I'm going to stop at 2. If I was to go back to my calculator, I can see that I would do second, vars, grab my CDF command, 1.4 and 2, and I get a final value of 0.8335 when I round to 4 places. So 0.8335. So using this sort of a calculator command really actually isn't that difficult. Hopefully this feels very similar in style to everything that we did with geometric and with binomial. The biggest key here again is to make sure that we understand the goal of every single Poisson distribution, which is that we're trying to represent the number of occurrences of something that happen in a given amount of time or space.